Hello guys, in this set of lectures we are going to have a recap on the mathematics that you're going to require in the course Analysis of Slender Structures. Specifically, we're going to review the differential equations that you're going to encounter during this course, and in the end we're going to have a recap on the matrices. Before going to the differential equations, let's take a look at the first fundamental theorem of calculus. Let's start with this simple example. Let's say we have a mountain such as this, and let's define a coordinate system too for it. Let's say this is x and this is y. Okay, so our mountain will start at somewhere at x equals a and goes all the way to x equals b. Let us say that we have a function which tells us the height of the mountain. The function is y equals f of x. So whatever x I put into this function, for instance this x, it will go ahead and give me the height of the mountain. Okay, so let us put a forest right after a mountain, forest, and a sea right before our mountain. This is a sea. Okay, so please take a note that this function, which tells us the height of the mountain, is only valid where the mountain actually is. So between A and B. Okay. So it is absolutely meaningless to ask what is the height of the mountain at some location x greater than b. Greater than b, we don't have a mountain. Or x less than a. Less than a, we have a c, we don't have a mountain. So this function is only valid between a and b. Okay. Okay, now let's ask a question. The question is how much we go up as we go from one side of the mountain to the other. Let's take a look at it. So this side, y is here, and on the other side, y is right here. So if we go from one side all the way to the other, we will go up as much as the value of delta y is. Let's see if we can find what the value of delta y is. Okay, by having this function, the height of the mountain, y equals f of x, we can give the answer to this question. Delta y is equal to f at the very top of the mountain, f of b, at the very end, f of b minus the height at the beginning of the mountain, f of a. Okay, that was very straightforward. But the problem is that normally this function y equals f of x is not at hand. Therefore, finding the height difference, or how much we go up the mountain, using this formula here that we derived, is not usually possible. But we have other means to find the height difference, the amount that we go up the mountain. Let me draw the mountain one more time. This is y, this is x. Okay, and let me draw the mountain right here. Okay, now let's bring this fellow to the picture. He's an observer. Okay, where did I put it? I put it up here. Okay, he's an observer. We're going to ask him to take a very, very close look at a portion of this mountain. Okay, you might want to ask me how close. I'm going to say very, 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 and we will define it mathematically. But at first, let me draw. Draw the bigger picture of this portion of this mountain. You see, let me draw the circle first. Okay, see, this mountain was essentially a curve, or it could be any, it could have any shape. But when you take a very, very close look at it, at the tiny portion, you wouldn't have a curve. You would essentially have a line. Let me just draw the line here. Okay, so this line is a part of the mountain. Okay, and now let's define what I mean by very, very close. I want to say that this distance here, I mean this size here, is very, very small. It is infinitesimally small. Let me name it dx. And dx is the smallest quantity that you can imagine. It is very, very small, but it is not zero. Okay, let me first draw our x-axis down here so that we know where we are. This is the x-axis, and let's say that we have gone all the way. I mean, the start of the axis could have been anywhere behind here. So let's say this could be the y-axis. And let's say that we are at some generic point x. It could be anywhere on the mountain. I mean, along the mountain. So now let me ask, and we have gone all the way to this size of it as dx, so this point here is x plus dx. Now let me ask the first question one more time, this time differently. The question is that how much we go up the mountain, this is a part of the mountain, how much we go up as we go from x, some point, to x plus dx. As we go infinitesimally forward, how much we go up? The answer is this value, and I'm going to call it dy. Okay, so let's take a look at it. What is the value for dy? It's very simple. If we could find the slope of this line, and this line, the function was y equals f of x. Let me get rid of this guy. So the function was y equals f of x, and the slope of that curve would be f prime of x. Okay, let me go down here again. I would like to argue that we could always ask this guy to take a look at our mountain and tells us f prime, the slope at every point. But we cannot easily find the function. We have to do something. But f prime is we can usually find it through observations, through laws of the universe, through mathematics. We could always find f prime. Okay. Let's say for a point of argument, let's say we have f prime and we would like to find f. Okay, let's start with here. Let's just go back to our question. My question was that how much we go up as we infinitesimally step forward. So the value of dy would be equal to the slope times how much we went forward. F prime of x times dx. Now let's see. If we go one tiny step forward, we'll go up by dy. How many tiny steps do we have to go from one side of the mountain all the way to the other? So many of them, infinite number of them. So let me see if I can add all of these dy's together to get delta y, which was the difference from this point to this point. Let me add all of the dy's up. So I would like to say that delta y, which was this height here, is equal to the summation of all of the dy's at every point. So let me just say dy, and I'll just name each one of the dy's by dy. For instance, 1, 2, 3, I name it I, and I starts from 1 to n. How many tiny steps do we have here? Our steps were infinitesimally small. They were very, very small. So we will have infinite number of steps in this domain here. Okay, so let's take a limit of this guy as n goes to infinity. Okay, you probably are familiar with this formula here. This is by definition integral. This is the integral of dy as we go from one point to the other. Our mountain started from A and went all the way to B. So you could probably name the range of this integral as starting from A and going all the way to B. Okay, so we have delta y equals integral of A to B dy. We also had okay, by the way, before I do that, let me fill in dy by this function that we found here. So we'll write everything down here. So our delta y from up here is equal to, I'm going to put dy into here, integral of A to B f prime of x dx. Okay. We also found that, previously found that if we have the function f, our delta y was equal to f of b minus f of a. Okay, so we have delta y at both sides, so these guys should be equal to, let me write down here, f of b minus f of a, this guy, is equal to this fellow, equal to integral of a to b f prime of x dx. And this is incidentally the first fundamental theorem of calculus. I think it's safe to say that we answered the first question. We figured out how much we go up the mountain as we go from one side of it, x equals a, to the other side, x equals b, and we figure out how much we go up by taking the integral of the derivative of our